right, good morning, chemists. We'll get started. So the plan is for today is to crawl our way through chapter 21, nuclear chemistry. This is the last chapter of Chem 1220. I know in the syllabus I have written that we would have covered chapter 23, but chapter 23, transition metals, is just one of my favorite topics, but it's not covered on the final exam. So I've decided to just spend more time reviewing and slowly finishing what is going to be assessed on the final exam. Maybe I'll show a demo from chapter 23 next week just to kind of show you what it's about. And really, I'm sad that I have to drop chapter 23 because it's really the reason why I got into chemistry. So I'll show you the demo that really excites me about chemistry. But we're going to be talking about nuclear chemistry. Just for a little bit today, we'll only get through like 10 slides and then move on to doing midterm 4 review, which our midterm is tomorrow in recitation. Nuclear chemistry is, this chapter is actually just a lot of review, and it's kind of fun and a simpler one. There's not a lot of math, and it's already math that you know. But this concept and topic is important because it's utilized in our everyday life in a lot of different ways that you might not have realized. So it'll give you some context of, some of the uses and application of nuclear chemistry out there. But yes, this is the last chapter, and then, majority of you, I'm assuming, is off to organic chemistry. So we only have 3 lectures left, including today. You're almost there at the end of the tunnel. So just take a moment and look back at how far you've come until now. This last chapter is like our swan song because it's rather fun. We'll talk about bombs and Barbie. So nuclear chemistry, I taught 1220 over the summer, right when Oppenheimer came out, and then there was a lot of buzz when we were learning about it, and gave context to the movie. I personally did not see the movie. I went to see Barbie instead, which was great. Maybe I should I go watch Oppenheimer? Yeah, okay. All right, yeah, I should, especially since I'm teaching about it. At the end, we'll talk about bombs, which I'm assuming gives more context to the movie. So yeah, maybe really I should watch the movie. So we'll talk about radioactivity, nuclear equations, types of nuclear reactions. There's actually different kinds and how they're utilized in application. So for what, a year now, right? Chem 1210, 1220. We've talked about chemical reactions, and there was a moment in my undergraduate that imprinted on me. One of my instructors said something to me. You know how I'm always very careful with the language I use? In your lab reports, when you write something, you want to be careful with your language to make sure that you're conveying what you want the reader to understand. One of my professors kind of scolded us on one of our lab reports because we would use language like, oh, I created this compound or something. And he's like, no, you did not create anything. He said, as chemists, we don't create compounds, only God can do that. I'm not religious, but it still impacted on me what he was saying. But as chemists, all we do is merely rearrange atoms, make new bonds, to make it into other things. We don't create anything. We just rearrange things like Legos. But in this chapter, nuclear chemistry, we actually are creating new substances. We are turning one element to another. So no, we're not playing God, but in this chapter, we can, in fact, use the language. We are creating new substances to something else. This is kind of the flag in the sand here that we're looking at different types of chemical reactions that have different rules. And actually, they're not chemical reactions, they're nuclear reactions that are quite different because they're occurring within the atom's nucleus itself. We're no longer just talking about bonds, we're talking about really high energy nuclear reactions. And so when we think about nuclear chemistry, we think of the movie Oppenheimer, which was based in building nuclear warfare. Think about nuclear power plants and all the folks involved with that. So let's just go with it. Yeah. So that always imprinted on me to just be careful with my language. We don't create anything. So if you want an alternative, right? Instead of saying like, oh, I created this compound. You can say instead, you can say you synthesized something. Okay, I synthesized something. Doesn't that sound fancier and like smarter than I created it? Because there's like this magical connotation that like you created it out of nothing, but that's not true. You just rearranged the bonds. So instead you can say I synthesized, or maybe I designed a compound or something like that. Okay, so nuclear reactions. We've got to do a little bit of review. And that is atomic symbols. This is review from Chem 1210, where we can describe what is in our atom. Every atom has 3 subatomic particles: protons, neutrons, electrons. And we can tell a reader what kind of atom we're talking about and its composition using an atomic symbol. All right, so, but for the most part, nuclear reactions, we're talking about kind of changes that happen in the nucleus. So remember that the nucleus contains your protons and your neutrons, right? All your protons and neutrons are kind of like in the center of your nucleus, while your electrons are just like crazy idiots in the cloud around it, in those different orbitals. So the electrons are on the outside, but those protons and neutrons are inside that nucleus. So, our atomic symbols tell us a lot about the composition of our atom. Some review. Here's your chemical symbol from the periodic table telling you the identity of your element, but it also tells you how many protons are in your in the central of your atom. Up here in the top left corner, you have your mass number. This mass number tells you the entire mass of your nucleus. So this includes your protons and your neutrons. But since you know what element we're talking about, you know how much of that mass is contributed to protons. So in this symbol, it says this is carbon 12, where 12 is talking about the mass number. The 6 in this corner, the atomic number for carbon, technically isn't really necessary. It's kind of redundant because we know that carbon has 6 protons from the periodic table. So if you were just to write something like this, carbon 12, that would be perfectly fine as well. You could just from the periodic table fill in yourself, okay, that's carbon has 6 protons. All right, and so there's 3 equations that helps us kind of deconstruct the composition of our atom, where as long as you're given or you know some parts of this, either the number of protons or neutrons or mass number, you can figure out everything that's in your atom. Where atomic number, that's your identity of your atom. Identity, so whatever that symbol is. Your mass number is the sum of protons and neutrons in your nucleus, and your charge comes from the difference of protons and electrons. So looking at these symbols tell me, hopefully we can fill this out rather quickly with these different symbols. We have 2 different isotopes of hydrogen here. They're both hydrogen, so they both have 1 proton off the periodic table. And so we know that these 2 protons and neutrons numbers have to add up to the mass number. Mass number, other way. Mass number. So that means hydrogen 2 has how many neutrons? 1. And then hydrogen 3 has 2. Perfect. Number of electrons here, since there's no charge written on these symbols, we're going to go ahead and assume that they're both 0, so it's charge neutral, and so therefore the number of protons and electrons have to match here. So 1 electron each to counteract that positive charge from the 1 proton. And then finally the mass number was given, so 2 and 3. The last one, sodium 22 plus, so this is a cation. It's a +1 charge, so that'll affect the number of electrons. But we can fill in the rest of the table looking at where sodium is. There are 11 protons. Protons, neutrons have to add up to mass number, so there's also 11 neutrons. And then tell me how many electrons there are. Here, how many? I know it's early. So if the charge is +1 and there's 11 protons, we have 10 electrons. Perfect. All right. Oh, and the mass number is 22. I already gave that. All right. So hopefully that is just review. And you can pick that up rather quickly from your atomic symbols. So something to note here, we're going to be using these atomic symbols a lot in these nuclear equations. But for the most part, nothing that we're going to be talking about in the further slides have charge. Because these, so Like I said, nuclear reactions differ from chemical reactions. In chemical reactions, we really care about balancing your atoms on each side and the charge on each side. That's super important. That's one of the steps for balancing chemical reactions. But in nuclear reactions, we're actually just going to ignore electrons for the first time in our life. We're just going to ignore the charge for things. So none of the atomic symbols that you'll see here on out in this chapter will have charges. And the reason we can ignore them is because these are such high energy reactions that the assumption is that your atom is just going to grab whatever electrons it has around to make it more stable. So we're just going to be ignoring it for the most part. All right, so nuclear chemistry matters because it explains why we see certain atoms that we typically see. So like carbon-12 is the most common form of carbon that you interact with. If you grab a hunk of carbon, the majority of them are going to be carbon-12. So the question is why? Why do we see 12 over other isotopes of carbon? Why don't we see more carbon-13 or 14 or whatever? And the reason is because of stability. Is that if carbon-13 or 14 exists, it only exists for a short time before it decomposes radioactively into something else. So we're going to be looking at the instability of some of these radioisotopes. So the nuclei we don't see in nature are typically unstable and they spontaneously just convert to something else that is more stable. So the things that we interact with on an everyday life we see because they are stable for the most part. And so all of these unstable isotopes decompose spontaneously and emit some type of radiation. Here are some of the different radiation types that we're going to talk about: alpha, beta, gamma. Here's just a summary of all of them, but we'll go through all of them in the following slides. So the first one is an alpha particle. So an alpha particle is just a helium nuclei. So if we remember, helium, here is your chemical symbol for helium. So helium has 2 protons, a total mass number of 4. So it has 2 protons and 2 neutrons. But since it's a nuclei, it has no electrons. So technically, this helium nuclei has a +2 charge. But like I said, in nuclear reactions, we typically ignore electrons. So when we talk about an alpha particle, we typically just symbolize it like this with the 4 and the 2 for your mass number and number of protons, and we use the alpha symbol to mean, hey, this is an alpha particle, it's just a helium nuclei. Technically it has a positive charge, but we're just going to ignore it for the most part when we balance things. Because in the next slide, or next section here, I say, all right, I'm telling you uranium-238 is an alpha emitter. So remember, when I give you an element and I put a number at the end, this number is always the mass number, where from the element name you can infer how many protons are present. So since it's uranium, what is uranium? I need my periodic table. Uranium is, so that's a symbol U. It has 92 protons. So I don't need to tell you that explicitly because you can always just look it up on your periodic table. But together with the mass number, we should know how many neutrons there are. And so if I tell you that uranium-238 is an alpha emitter, if we write a nuclear reaction to describe this, if something is being emitted, is it a reactant or is it a product if it's being emitted? It's a product, yeah, just like when heat is released. So just think of emitted as like released. It means that thing is a product. And so this language is helpful because that tells us, if I know an alpha particle is emitted, that alpha particle is going to be a product. And so I'm going to put uranium-238 as my reactant, and now it's just simply balancing the numbers and determining what is the identity of the thing that has to be left, so all of the protons and neutrons are conserved here. So I like to just, what you're doing is basically balancing these numbers that kind of are on the sides of your particles here. But the most important thing for this first thing is that knowing that this is an emitter, and so you put that alpha particle on the right side. So just kind of looking at the numbers, the missing mass number of the missing piece here is 234. So whatever's left over has to have a mass number of 234, but then how many protons does it have? 90. Yeah, and so now both sides add up to the correct mass number and number of protons. So this is kind of a more straightforward balancing, but very different than other chemical reaction balancing that we've done before. And so now that we know the number of protons, we can identify what element it is. What is it? TH, yes, which is thorium. So we can say that uranium, when it emits an alpha particle, becomes a thorium atom. So yes, we created, or I guess, we created this new thing. We created thorium in this case. We were able to change the identity of the element via a nuclear reaction. We've never done that before. All chemical reactions, all we did was change the identity of the compound. It was the same atoms, but now we're actually creating new things. All right, so let's write the balanced equation for the alpha emission of curium-242. So if you look closely on your periodic table and look for curium, it's Cm, all right, on the periodic table. So I can recognize that curium is going to be my reactant, so Cm. And from this, since I tell you it's curium-242, the mass number is 242, and then from the periodic table, I know curium has 96 protons. And so we do it the exact same, just balance those mass numbers and protons on each side. So if curium releases that alpha particle, what's left behind is something with a mass of 238 and 94. And so we look and see on our periodic table, that is element Pu, or plutonium. And so we can say, all right, when curium undergoes alpha emission, where alpha particle is the product, it converts to plutonium. All right. So that's basically balancing, and all balancing will do that. Oh, and again, I mentioned here that, again, we ignore electrons altogether. All we're doing is focusing on the protons and neutrons, because the assumption is that electrons will just come and go as they please, because these are really high energy reactions. All right, beta particles are a little bit different. They have a different type of atomic symbol, but this atomic symbol really helps us balance things. So a beta particle is essentially a high energy electron. But this electron isn't the same electrons that are on the outside of our atom that we know. These beta particles are typically emitted by neutrons. So a neutron basically throws off a negative charge, and when that neutron does that, it gets converted to a proton. So we can change the identity of a neutron to a proton, and therefore we can change the identity of our element. So some details about a beta particle: there's no mass here, because if you look at the symbols, it has a negative charge, so basically it's the opposite of a proton, but the mass number is 0. But we still balance it the exact same within our nuclear equations. So I mentioned when a nucleus emits a beta particle, a neutron is what's emitting that beta particle. And so if you just balance this, just like we did before, we want to make sure those mass numbers match, so whatever is left over has a mass number of 1. But what is the charge here for a number of protons? It would be +1, because +1 and -1 give us 0 to give us our neutron. And so if you think about, well, what is this? What has a charge of 1 and a mass number of 1? Well, that is a proton. And so here we just proved when a neutron emits a beta particle, it gets converted to a proton. So it becomes something new. And so again, be careful with language here. These different substances are beta emitters. So since they're emitters, the beta particle is going to be the product, and we balance it the exact same. So ruthenium-106, when it emits a beta particle, the mass number that's left behind is still 106, because a beta particle does not have any mass, but it does have charge. So what is the number of protons left behind to make it all balanced? 45, yes. And so what element is that? You look on your handy dandy periodic table, and it gets converted to 40. Where's 45? RH, there we go, rhodium. It gets converted to rhodium. Same thing with magnesium 28. So there is your reactant, magnesium-28. It's emitting a beta particle, so you have to here, I'm forcing you to put in, okay, the beta particle is the product, and so what is left behind. Here I didn't tell you the number of protons of magnesium, but you can just figure it out yourself. There's 12. And then balance it so all those numbers match on each side. So whatever is left behind has a mass number of 28 and 13 protons. So what is that? Aluminum. All right, so when when magnesium emits a beta particle, converts a neutron to a proton, what happens is that it converts to a new element. It's now an aluminum atom. All right. Okay, and so yeah, we're ignoring electrons. Oh, and yeah, ignore states. Everything probably is either happening in the gaseous state or the solid state because, again, these are very high energy reactions. Okay, last type of radiation source is a gamma ray. So note how I said alpha particle, beta particle. Those two things have, I guess, some mass. Alpha particle has a lot of mass. It's a helium nucleus. Beta particles are an electron. Electrons do have a tiny, tiny bit of mass within there. But gamma rays are not a particle at all. Gamma rays are actually just pure energy. It's just a big ball of energy. So the symbol we use to signify a gamma ray is the gamma symbol, 0 in the mass number because there's absolutely no mass, but there's also no charge either, right? So a gamma ray is just literally electromagnetic radiation. If you remember our electromagnetic spectrum, gamma ray was like way, way, way at the high energy region on the opposite side of like radio and microwaves. So some substances undergo gamma radiation as well, but you might be thinking, well, if it's 0 and 0 in the mass number of protons, balancing should be easy, right? That it's 0 and 0, it'll be balanced on each side, whether when you put that gamma ray as your product. So there's a few things that undergo gamma ray radiation, and typically these substances are symbolized with a M within their mass number, where M means metastable. So technetium-98 is a common gamma ray emitter, and this is actually used in hospitals to be a gamma ray radiation source for some types of health detection methods that they need technetium and their gamma rays in order to do the types of tests that they need to do. And so they have to get metastable technetium-98. And so the decay process that happens with gamma ray emission is that just a more stable, non-metastable state technetium is produced. So you see here when we balance this, the little m just goes away. We basically started with a really highly unstable technetium-98. It releases a gamma ray and it's still technetium-98. It's just a little bit more stable, right? So the m just signifies metastable and it'll emit a gamma ray. So gamma rays, again, pure energy, come from just highly unstable nuclei, but the identity of the thing doesn't change. All right, so just a couple, like 2 more slides, and then we'll do some review. All right, so we talked about 3 different radiation sources: alpha, beta, and gamma. So if we think about those radiation sources, let's draw the symbol. So an alpha particle has a mass number of 4. And has 2 protons. A beta particle has a mass number of 0 and a negative charge, and then gamma rays are just a pure ball of energy. So when we think about how these types of radiation interact with us, like our bodies or the materials around us in our world, if we think about how these particles differ, it can explain some of the observations that we see. Alpha particles, they have a lot of mass. A lot of mass. So when you think about an alpha particle like penetrating our skin or something, it's like just throwing out a ping pong ball at you. I mean, it's a high energy ping pong ball, but if I throw a ping pong ball at you, it just bounces off. And that's exactly what alpha particles do because they have a lot of mass. right? That they just bounce off our skin. They are stopped by just a hand or even a piece of paper, all right? Alpha particles will be stopped by pretty much anything because they have a lot of mass within there. Beta particles, on the other hand, they're negatively charged and they have a very, very small mass, little to no mass, basically, small, no mass, because it's essentially just an electron. And so beta particles penetrate further within our bodies, that a beta particle will actually go through our hand or through our skin, at least a little bit. But because it's an electron, it does have a little bit of mass, it will eventually be stopped by something like a thick aluminum block or something, all right? That beta particles can be stopped eventually because they do have a little bit of mass. Gamma rays, on the other hand, have no mass at all. No mass, just a lot of energy. All right, so these gamma particles are basically like a gunshot wound to all of these different materials because there's no mass to actually stop it, that it's just pure energy. And so gamma rays will not only go through skin, thin sheets of metal, you actually need, it'll be stopped by really, really thick concrete. So in this case, beta particles can be stopped by a lead sheet. So something thick enough, something really, really dense can stop a beta particle eventually, but gamma rays will just go right through that lead sheet. It needs something a lot thicker, like a big encasement of concrete in order to stop gamma radiation. And again, it's because there's no mass. It's essentially this invisible thing that is just tons of energy that will penetrate through lots of different materials. And so the extent of these different types of radiation have different implications on our life, depending on where these radiation sources exist, how they're protected from the environment, affect their level of danger, or how they're utilized in application. All three of these radiation sources are technically still, so yes, if you look at this, it looks like, oh, alpha particles aren't super dangerous because they just like bounce off our bodies. But all three of these radiation sources have enough energy to what is called ionize water, meaning rip off an electron on water. And that is what can make any type of radiation source rather dangerous, because we are big water bags. And so if we have too much alpha particle radiation, even though it doesn't penetrate our skin, it can still interact with water. And so that's where the danger comes from. Ionizing water can be dangerous because if you take water and ionize it, basically expose it to energy, this could be an alpha particle, beta, or gamma, it doesn't matter, all three of them will do it. It'll rip off an electron on that water. Now you have this really high energy electron that can go off and do other things. But also that positive charged water is also really dangerous in that it can react with another water molecule and rip off a hydrogen off of another water molecule. And so what you see here, when I balance this equation, I'm left with an OH molecule, but note that it's charge neutral, all right? It's charge neutral. So this OH is different. It's not the same as hydroxide. Hydroxide is just base. OH is different. Notice that I didn't put a charge. It's not that I forgot it. No, OH is actually a free radical. It's missing an additional electron. OH, free radical, is OH with literally only 7 electrons in that valence shell. And this is really dangerous. This free radical right there, all right, can go and break chemical bonds within our bodies. It can break tissue, it can break proteins, all of those things. It can break DNA, and that free radical is what causes sickness from radiation. Too much radiation is due to the ionizing of water, and all of these radiation sources can do that. But again, depending on how these sources are contained, make the level of danger different, which we'll talk about in the next slides, and then we'll be done with this. So yeah, all these things, when they interact with water, is bad. Okay, so let's discuss it. So keep that in mind, how radiation sources interact with our bodies and with the materials around you, all right? Okay, so your friend learns that household smoke detectors contain a radioactive material, americium-241. all right? And it's radioactive. And your friend's like, oh no, radioactivity's bad, so I'm gonna get rid of all of my smoke detectors in my house. Right? Because radioactivity is bad. We just talked about all that like bad ionizing water and stuff. Like, I don't want that near me and my family. So I'm gonna get rid of all my smoke detectors. So I'm telling you that americium-241 is an alpha emitter. Where do we put our smoke detectors? We just put them on the ceiling, right? Okay. So can you come up with a plausible explanation to tell your friend, once you now know that americium-241 is an alpha emitter, to convince them to reinstall their smoke detectors? Why don't you take a minute and discuss with someone around you why they should install their smoke detectors using the concepts we learned today, the chemistry concepts learned today, right? This radioactive substance is an alpha emitter. Why should they reinstall their smoke detectors? All right, does anyone want to share? Does anyone want to convince me to reinstall my smoke detector? Anyone want to share? Anyone? No? No? No one? Yeah, go ahead. Okay, so we pointed out that alpha particles have a lot of mass, but they're not super dangerous. But put that into the context that like a normal person on the street would understand. Yeah. Oh, absolutely, yeah. The concern is, oh, my house is on fire now. I need to know now than a little bit of radiation. So what I want everyone to think about is, okay, the radiation source in that smoke detector is inside where? Do you want to share? It's inside something. It's not going to get to you. Right? If you look at the picture, the little bit of radioactivity is just inside the smoke detector, which is encased in plastic. So is that radiation actually going to get outside of that radiation, outside of the smoke detector? No, it's not. So it's not harmful. As long as you don't what? Break it open. As long as you don't break it open and start eating its parts, then it's not going to be a big issue. I know you laugh, but that's what the next slide is. All right? Okay. So yes. Please reinstall your smoke detectors. Yes, there's a little bit of radioactive material in it, but it's an alpha emitter, and it's encased in plastic and like metal shielding to prevent any of that radiation from leaking out. So again, also weigh the consequences here, the safety concerns. I want to know my house is burning down now, rather than the small chance that a little bit of radiation leaks out. Okay. That's what this next slide is, and we'll stop here then. And I mentioned, so what makes the smoke detector safe is that the little bit of alpha emitter radiation is inside that casing. But there's a story. I was in a book club for a while, but I was the only one reading the books, and it wasn't fun. And so in book club, we read the book Radium Girls. I actually didn't read it. I just did the audio book because I'm lazy. But Radium Girls, it's a story, so this is a true story of women in New Jersey back in 1920s. Like good watches, they always, absorb the sunlight and then like they glow in the dark, right? So when you are in the dark, you can still read your watch because of the glow. And so back then, before they learned about phosphorescent materials, they literally painted their watch dials with radium, or actually it was tritium, but it was I think it was radium. Yes, they painted the watch dials with a radioactive substance so it would glow an eerie green. All right, so these companies were painting their watch dials with radium-226. And so there's a bunch of young women that they hired to paint the numbers on watch dials. So that was their job. But think about painting a watch dial, like the numbers on a watch dial. Those are really, really small, right? So you have to use a really, really small, fine paintbrush to do it. So all of these women, they were literally painting with radium-226. And what they would do is they take the paintbrush, they'd put it between their lips to moisten the point of their paintbrush, dip it in the radium, and then paint it. And so all of these young women, they were dying like flies. First, like their jaw, they would lose all their teeth, and I'm talking like 20-year-olds, right? 20-year-old women, they would lose all of their teeth, and their jaws would fall off, and then they would die at like late 20s, early 30s or something like that. And so they didn't make the link to, oh, it's how they were handling the radium. They just thought it was a cool glow-in-the-dark paint. They would paint themselves with it, right? Like during their breaks, they would take the radium paint and paint faces on each other. But the research wasn't done, and it wasn't understood the dangers of radium, so much that the company was just trying to say, oh no, we're not at fault. These women were just promiscuous. They, are doing things outside of work that's causing them, all of these health issues and them dying at like 30. But no, it was in fact the radium and how they were using the paintbrushes and ingesting it essentially. So I hope you can see the difference here. Why is radium, which is also an alpha emitter, dangerous here? What's the difference between this story and our smoke detector? The difference is that they were actually ingesting it. Right? So they would take the radium, the alpha emitter, ingest it. Now you have an alpha emitter inside your body. Our bodies are big water bags, and then that is why those alpha emitters now interacting with water now makes it a much, much bigger problem once it gets inside your body. Then those alpha particles are like big grenades going off inside your body, and that's why these women were dying so young. So I do recommend reading or listening to that book. It's a really interesting story, and I think there's a movie about it too. I didn't watch the movie. Did anyone watch the movie? Was it good? Was it sad? Yeah, sad. Yes, and so that's the difference here. But again, radium-226 is also an alpha emitter. Okay, so we'll stop there at that nice note of alpha emission, and we'll come back to this next week, and again, kind of go through a slow pace of chapter 26. I'll show a demo next week, I guess. Okay, so we'll do midterm for review. Okay, got 40 minutes, so where do we leave off? Right here. Okay, so we're still on chapter 19 stuff. So yeah, if you don't have the packets right here, it's go.osu/1220rev4. Okay, so we left off here where we're talking about delta G. We talked about a bunch of different equations with delta G. And so to remind yourself, remember that supplemental information is already posted. So you, if you refer to that, you can see that there are a bunch of delta G equations you're given. One of them is delta G equals delta H minus T delta S. We've already used that one extensively in the previous questions we did on Tuesday. We also have delta G equals negative RT ln K, where the magnitude of delta G changes based upon if K is a big number or a small number. And then the last one is delta G equals delta G naught plus RT ln Q. We use this version of delta G when we're not at standard conditions. So if we have Q conditions, like some random conditions, and we want to predict does the reaction shift left or right in order to achieve equilibrium, this is the equation that we use. So if I tell you that the Ka of an acid is this, 1 times 10 to the negative 5, which equation should I use? The first one, second one, or third one? The second one. I give you a K. I give you a K value. So in this case, it's Ka, whatever. And so we want to be using this second equation to get what is the delta G naught of this reaction. This is just a different way to get the book value where we would do products minus reactants. Instead, we are just using the K value given. So simply, I am calculating delta G naught. So I'm going to be using negative RT ln K because I was given K. And I was given T. Since this is at standard conditions, it's at the temperature of 298. So it's just plug and chug. Delta G for this reaction is negative 8.314 joule mole Kelvin. Temperature is 298. And then ln K, in this case it's Ka, so 1 times 10 to the negative 5. But without even calculating it, based upon the value of K, what do you think the sign of delta G naught is going to be? Is it going to be positive or is it going to be negative? Positive, yeah, because K is a really small number. So the reaction doesn't move forward that much. So delta G is going to be a positive number. So to prove it to you, all these numbers multiplied together is 28.5 times 10 to the 3 joules, or that's 28.5 kilojoules per mole, right, based on that K value. And so yes, we have a positive delta G because K is small. That the forward reaction is not favored. The forward reaction is not very spontaneous. Okay, so that's relating delta G and K. And of course, this delta G is the same delta G you would calculate if you did delta H minus T delta S if you were given those values. Okay. What if we take this same solution, remember Ka is 1 times 10 to the negative 5. What if the solution is made to be this, 0.5, 0.5, 0.5 concentration? So the question is, are we at equilibrium at these conditions? We are not. If I give you concentrations, what you should think is, okay, I'm probably not at equilibrium. I should probably calculate Q here. Right? So this is really no different than chapter 15 or 16 when we'd compare Q and K, but we're using delta G to get the answer instead. So Q for this reaction, for any Ka expression, remember, is H plus concentration, A minus concentration over HA concentration. Remember, the reaction that's happening is HA, equilibrium, H plus, A minus. Remember that? Weak acid. Okay. And so in this case, we just take that Ka expression and insert all those numbers that are actually given. So 0.5 squared over 0.5. So I think Q is 0.5. Is that right? So that's Q. So let's just predict without calculating delta G. If Q is equal to 0.5 and K is equal to 1 times 10 to the negative 5, Q is bigger than K. So which way does the reaction need to shift? Forward or in reverse? In reverse, yes. I like to think, oh, Q is bigger, so I have too much product. So I have to go in reverse. So what should the sign of delta G at this moment be if the reaction goes in reverse? It should be what value? Positive or negative? Positive, yes, if the reverse reaction is spontaneous. But let's check it for ourselves. All right, so I am calculating delta G. This is not a mistake. I didn't just forget to put the naught. No, I want you to calculate delta G at these non-standard conditions. So we're going to use the other equation, delta G equals delta G naught plus RT ln Q. We just calculated Q, R is a constant, we know temperature, and we got delta G naught from the previous question. So we're basically trying to calculate what is delta G at these conditions. So delta G at standard conditions we got previously was 28.5 kilojoules, but this should be in joules because R is in joules, so plus 8.314, 298, ln Q, we just got Q as 0.5. And so if I do this part, the ln Q, so the RT ln Q, 298 times ln 0.5, I get that this number is negative 1717. All right, and so yeah, if you add up these two numbers, delta G is still a positive number. So the reaction still is spontaneous in the reverse direction at these conditions. Again, because Q is greater than K. If it were the other way, let's say if Q was less than K, that means I don't have enough products. I have too much reactant. So delta G would be a negative number would come out when Q is less than K. right? So that's just relating it back to previous concepts from all the way back, chapter 15. Okay, all right, so how do we feel about 19? We good? Okay, all right. All right, so electrochem. Perfect, all right. I love electrochem. It's so applicable, but I like nuclear chemistry too. I think it's fun. The balancing of the equations is fun, I think, because it's easy. Okay, so I have 4 different reactions here. What kind of, 3. What kind of reactions are these? Based upon how they're written. The substance is doing what to that electron? It's gaining the electron. So these reactions, what kind of half reaction is it? Reduction or oxidation? Reduction, yes, it is reduction because the electron is the reactant. The reactant's gaining that electron. And what's the saying? Leo goes Gur. Loss of electrons is oxidation. Gain of electrons is reduction. So here A plus is gaining the electron, so that means A plus is being reduced. You can also tell from the oxidation numbers. They're all going from +1 to 0. They're all being reduced. And look, I have all these reduction potentials here. So based upon these numbers that I give you, B plus is a what? Stronger or weaker oxidizing agent than C plus. So obviously we are comparing the B and the C reactions, but we want to be careful of what the question is asking. So it's asking which one's the stronger oxidizing agent. So when something's an oxidizing agent, what does it do in the reaction? It gets reduced. Yes, so really what this question is asking is, excuse me, which one is more easily reduced? So I want to look at the most positive reduction potential. So which one has the more positive reduction potential? B plus or C plus? C plus, so therefore B plus is a weaker oxidizing agent. It's a weaker oxidizing agent because it's less easily reduced. So think about how else I can ask the question. Instead of asking about reducing agents, oxidizing agents, I can ask about reducing agents instead, right? So again, change the language so it's easier to interpret and use the reduction half reactions to help you. So A solid is a what? Stronger or weaker reducing agent than B. So if we're talking about reducing agents, things that are reducing agents do what in a reaction? They are actually oxidized. So really this question is asking which one is more easily oxidized. So can I just look at these reduction potential values as is? No, you can't. If I'm looking at which one's more easily oxidized, technically you need to look for which one has the more positive oxidation potential. Oxidation potentials are the inverse or the opposite sign of your reduction potential. So you could go ahead and make a new column here. The oxidation potentials of all of these reactions is -0.1, -0.2, -0.3. Right? But these oxidation reactions, they don't describe the forward reaction. They actually describe the reverse direction. Yes. So in these oxidation reactions, you actually need to read the reaction backwards. That in these oxidation reactions, the solid is now the reactant. A solid is being converted, oxidized to A plus. So that's why the language changes here. See how I'm saying, compare the oxidation of A solid to B solid? All right, so that's why that changed a little bit. Right, so what would the answer be? A solid is a what? Stronger or weaker reducing agent? Or is it more or less easily oxidized than B plus? It would be stronger, yes, because it is less negative. Again, we're looking for the more positive oxidation value. So in this case, since A plus is the crappier oxidizing agent, A solid is going to be a better reducing agent. Remember that kind of language? Yeah, it works here too. Okay, so, okay. All right, based upon the same 3 reactions, which of these reactions are spontaneous? So if I'm looking for spontaneous, so now it's not half reactions. Now I'm actually combining half reactions. I'm making a full electrochemical cell. If I'm asking you about spontaneity, really what I'm asking you to do is tell me, is E cell positive or not? So you just need to calculate it. But how we calculate E cell is tricky. You have to take the reduction potential of your cathode and subtract the reduction potential of your anode. Both of them are in the reduction form, so you're just using these numbers as is, as they're given. So E cell equals reduction potential of your cathode minus reduction potential of your anode. So in all of these questions, these options, you have to decide what is the cathode and what is the anode, and some of the substances change. And so to determine if something is your cathode or anode, just remember the mnemonic N, ox, red, cat. Whatever is oxidized is your anode, whatever is reduced is your cathode. So the best mode of strategy here is to get those oxidation numbers. So A plus is going from +1 to 0. So A is our what? Anode or cathode? Well, 1, A plus is being reduced, so it's going to be our cathode. B, on the other hand, its oxidation number is going up, so it is being oxidized, so it is our anode. So when we do the math for E cell, we're going to take whatever A's reduction potential is and subtract it from B's reduction potential. So this one is going to be 0.1 minus 0.2. So is this spontaneous? No, it's not, because a negative number comes out. All right, we do the same again. So C plus to C, that is our cathode because its oxidation number is going down. A solid to A plus, that is being oxidized, so it is our anode. So when we do E cell again, it's cathode minus anode. So it's C, whatever number C is, so 0.3, minus the reduction potential at the anode, so 0.1. So is this reaction spontaneous? Yes, it is. This combination is spontaneous. All right, and then the last one, B plus to C. And so, yeah, B plus is being reduced, so it is the cathode, and then C is my anode. And so when we calculate E cell for this last one, it's going to be the B reduction potential, so 0.2, minus the reduction potential at C, so 0.3. So this one is not spontaneous because a negative number comes out, right? What if we reversed this last reaction? So here I'm mixing B cation and C solid. It's not spontaneous. But what if I mixed C plus and B solid? Would that be spontaneous? That would be. Let's check it. Let's check it. All right, so let's just do that example. Let's rewrite this reaction in the reverse direction. B solid combines with C plus to give B plus and C. So now B is being oxidized. So it is now the anode. C plus is being reduced. Its oxidation number, its charge is going down, so it is the cathode. So now when you do the math, C is the cathode. Where are my numbers? C is the cathode, so E cell is 0.3 minus 0.2. So here, the reverse reaction is spontaneous because you've changed the identity of your cathode and anode, right? You've swapped them. Good? All right. Okay. All right, so more review. Okay, in an electrochemical cell, maybe I should have done this first. Oxidation occurs at the, which one? Anode. Reduction occurs at the cathode. Electrons flow from where to where? Anode to cathode. Anode to cathode. Perfect. And the reason is because in an oxidation reaction, electrons are lost. They're a product. And those products funnel directly into the reactant side of a reduction reaction. So that's why they flow from anode to cathode. Okay, so here's a half reaction. So here's different ways we ask the same questions is, okay, here's your half reaction. What half reaction is occurring at the anode? So really, remember, anode means oxidation. So really this question is asking what thing is oxidized, write the half reaction for that oxidation. So we can go ahead and get those oxidation numbers to help us. Again, remember, it's basically charge except where like neutral elements have a oxidation number of 0. So here A plus is +1, C solid is 0, A solid is 0, C plus is +1. So we see A is being reduced. So that is the reaction at the cathode. And then C solid is being oxidized. That is at the anode. All right? But we actually want to write the half reaction. So we're going to split it up. And we need to make sure that it's balanced. So at the anode, we're going to have the C components because it's what's being oxidized. So we have C solid becoming C plus. Is that balanced? Is that it? Am I done? Nope. What's missing? 1 electron. Now it's balanced. Then at the cathode, it's just A. So A plus goes to A solid. Is that balanced? No, it's not. So you put the electron on the reactant side. So I hope you see, look, we have a nice current forming because at the anode we are producing electrons and it's feeding directly into that cathode. So here you clearly see that electrons flow from the anode to the cathode, and it's because oxidation occurs at the anode, reduction occurs at the cathode. All right. Okay, so over time, how do the following things change? So let me just bring this reaction down here so we can see it. Okay, here's the reaction. I'll change the color so you can see it better. We'll make it green. All right, so this reaction, let's say it's spontaneous and it's occurring over time. How do these things change over time? Because remember, a reaction is happening. It's moving in the forward direction. So as this reaction flows and runs, how does the concentration of A plus change? It goes up or down or doesn't change? It goes down because A plus is a reactant. It's right here. In order for the reaction to move forward in the spontaneous direction, in the forward direction, you have to consume A plus. So that concentration is going to go down. C plus, on the other hand, is going to change. How? It's going to go up because it is a product. How does the mass of A change? Mass of A solid change? It's going to go how? It's going to go up because it's a product. Yep, and then C mass is going to go down. Perfect. Are you guys doing VOL this week? Yeah, okay, perfect. So does this help? Kind of? All right. Okay, so these things are changing over time as the reaction moves forward. So how does Q change? At standard conditions, Q is 1. Everything starts at 1 molarity. All right? So when we hook the cell together up at standard conditions, A plus starts at 1 molarity. C plus starts at 1 molarity. But you just told me that over time, A plus concentration starts to dip down. C plus starts to move up. So how does that affect Q? Let's just check it for ourselves. Q, just getting the expression for it, it's products over reactants, is C plus concentration over A plus concentration. So put these trends into Q. How does Q change over time? It goes up. Yes, it goes up. Q goes up. I have to look at it. I don't memorize things like that. I just look at the trends and be like, oh yeah, these things change this way. Q has to go up as the reaction moves forward. Or think about it this way. Oh my gosh, I'm so stupid. I should just be teaching it this way. Okay, Q, right? The larger Q is, you have more what present? Products, right? As the reaction moves forward, you create more products and less reactants. So yeah, you're just making more products. So Q is going to get bigger and bigger and bigger because this reaction is moving forward, forward, forward. You're making more products. That's another way to think of it too. Yeah. But also the concentrations are consistent with that as well. Okay. So Q is changing at over time. So that's a misconception, is that, okay, you plug in a battery, that voltage isn't going to stay that same voltage the entire time. And the reason is because concentrations are changing. Voltage does change over time. It's going to start to drop and drop and drop as your concentrations change. So how does the voltage, the actual measured voltage of your cell, change over time? If Q gets bigger, this Q gets bigger, this entire term gets bigger, but we're subtracting it. So over time, your measured E cell is going to decrease, yes, until your battery is 0 volts and it's dead. It's absolutely dead, right? Does the value of E cell not ever change? No, that is a table value. That's products minus, or not, it's cathode minus anode, right? And you just calculate that, and those standard conditions are 1 molarity of everything. But the Q conditions is how we account for the concentrations that are actually there. All right, so yes, E cell dips down as your reaction proceeds forward, all right? And think about it. Don't like try to say, oh, the voltage goes up over time. That doesn't make sense. You're saying, oh, you plug in a battery and it like gets more powerful and more powerful and more powerful as you like plug it in. No, that doesn't make sense. They get weaker and weaker and weaker as we spend them. Okay. All right, oxidation numbers, get all of them. For oxidation numbers, what should you think? Just charge. If you just think charge, you'll be fine. All right, so magnesium, 0. Magnesium chloride, Mg is +2, chloride is -1. Permanganate. So what's the trick here? Which one do you already know? Oxygen, when it's in a compound, is -2, all right? So that means all those oxygens are -8, so manganese has to be +7, right? This different manganese, these oxygens are still -2, but there's only 2 of them now, so there's -4, and so this manganese actually has a +4 oxidation number. So these 2 manganeses have different oxidation numbers because they're different compounds, different number of oxygens attached to it. Okay, this one, IO3 minus. Again, the oxygen is what helps us. So -2 for oxygen, -6. So that means that I is +5. Sodium sulfate, there's a lot of stuff going on here, but again, charge is going to help us. You can also split it up into its ions, right? Sodium is always +1, sulfate is always -2. So we can kind of split it up and the oxidation numbers will still work here. Each of those sodiums are +1. Sulfate, on the other hand, each of those oxygens is -2. So the oxygens, the 4 of them, are contributing a -8. And so that sulfur has to be a +6. So if you go through this entire compound, there's 2 sodiums. So that's 2 times +1. Plus 1 sulfur, which is a +6, which we just said, plus 4 oxygens, which we just said was -2. So if you add all of those numbers up, you should get 0. Yes, so all of those oxidation numbers do work, even if you split them up into the individual ions as well. Okay, good, oxidation numbers. Maybe I should have started with that slide. Oh well. Okay. So let's talk about electrochemical cells, voltaic cells, right? So yeah, you have your anode over here, you have your cathode over here. Our electrons move this way. But in order for the circuit to be complete, what am I missing? The salt bridge, yes. You need to actually connect the 2 compartments, not only with a wire that allows electrons to flow, but you need that salt bridge to allow charge balance to occur in the 2 compartments. All right? So the purpose of the salt bridge is to allow ions to move freely left to right to balance the charge in the 2 compartments. So in the anode, if you think about like a oxidation reaction, so let me just write a generic oxidation reaction. So a generic one would be like A goes to A plus and an electron. So as an oxidation reaction moves in the forward direction, you start to accumulate positive charge. See how positive charge accumulates in that anode? Because you're making more products, you're making cations. So in order to balance that positive charge, anions are going to move towards the anode to balance that positive charge that you're accumulating. On the other hand, in the cathode side of the reaction, reduction is happening. So a generic reduction reaction would be like A plus, an electron gives you A solid. So in this reaction, you're consuming cations. You're making it less positive. So here, I guess negative charge is accumulating, okay, more negative charges. And so all of the cations are going to move towards the cathode to try to neutralize that, because you're getting rid of cations and replacing it with something that's neutral. So you're going to replace it with the salts from your salt bridge. Typically, there's an electrolyte present. That cations will move towards that cathode, all right? But that's the reasoning. If you just want to memorize anions go to the anode, cations go to the cathode, that's fine, but there's a reason behind it. Okay. All right, keep going. All right. If delta G naught is very negative, the reaction is what? Spontaneous or non-spontaneous? Spontaneous. What does that mean about delta S of the universe also, for fun? It has to be positive. Yes, they are related to one another. All right. But then what does that mean about the cell potential? It's going to be positive. And K is going to be what? Big. Yeah, if the forward reaction is spontaneous, you make a lot of products automatically, spontaneously, then K is going to be big. And so all of the reactions that relate all of this together is delta G equals negative RT ln K. And so you see, oh, as K increases, delta G gets more negative. But also, delta G equals negative NFE. We see that as the cell potential increases, delta G also gets more negative because of that negative sign. So if we can combine and set these two delta G's equal to one another, you can see that K and E are related to one another as well. I think if you move this around, you get RT ln K equals NFE. So you get that your cell potential equals RT NF ln K. Something like that. All right. So yeah, you can see, okay, as E is more positive, K is bigger. All of these things are related to one another. All right. Good. All right. And yeah, that's just utilizing the equations that you're given. All right, let's keep going. All right, so for this redox reaction, I tell you the cell potential because it's made up, but you can calculate it. You just do cathode minus anode. For this reaction, what is N? So here, remember, N is the number of electrons involved in the process. When you have a half reaction, it's quite obvious because electrons are literally there in the half reaction. But when you already have a balanced redox reaction, it's a little bit more complicated because those electrons got canceled out in the background. So you kind of have to backwards think, what were the electrons canceled in the background? So the best way to do this is to use oxidation numbers to help you, because those oxidation numbers relate to the number of electrons that were transferred. I'm going to focus on Z because Z, there's only one of them, and it's quite straightforward that Z is going from 0 to +2. So in my mind, oh, I needed 2 electrons to do that, right? Where did those electrons come from? They came from X. Oh, wait, this is not a right. Okay, sorry. That should be an X. That should be an X. So please fix that in your thing. So yeah, the question is, well, where did those electrons come from? Well, they came from X, but you might be thinking, oh, but X, it's going from a +1 to 0 oxidation number. Isn't that just one electron involved? What's the difference here? There's two X's. So there's two X's losing one or gaining one electron each. So yes, that just X plus to X involves one electron, but there's two of them. So basically that reaction was multiplied by 2 to make the two electrons cancel out and match when you re-add those half reactions. So this total process also requires 2 electrons because you're actually reducing 2 X atoms, not just 1. And so N here is equal to 2. All right. So you don't have to totally deconstruct the half reactions to figure out what N is. You just have to look closely at the charges and make sure that it matches here. All right, so based upon this information, calculate delta G. So here we're going to use the equation negative NFE cell. Because I gave you E cell, we just calculated N, and we're solving for delta G naught. So it's fine to use E cell naught. The only missing piece was that N value that we just got. So it's just plug and chug here. So negative 2 electrons, Faraday's constant 96485 coulombs per mole of electrons, and then E cell positive 1.2 volts. And again, a coulomb volt is a joule. So just put in Faraday's constant, put in E as is, and you'll get a joule out, I promise. So 2 times times 1.5, I get negative 231.5 times 10 to the 3 joules. Okay, so negative 200 joules, that's a lot. Okay, so yeah, this reaction, very spontaneous, very negative, but it makes sense because E is very positive. Okay, so with that delta G we just got, how do we get K? Let's use the other equation, delta G equals negative RT ln K. We just got delta G using E cell. R is a constant, we know T, we can calculate K. So you can either use this equation or you can use the other equation that I derived myself, where I combined the 2 delta G reactions and made K relate directly to E. You can use that one as well. Yeah, so, but let's just use the delta G version instead. Doesn't really matter. So here we're going to solve for K. So negative 231.5 times 10 to the 3 joules equals negative R 8.314, temperature 298, and then ln K. So solve for K. So that number, nice, I still have it in my calculator, 298. So I get that ln K is equal to 93.5, so E to the both sides, and I get a real big number. I get K is equal to 3.9 times 10 to the 4, 40. Dang, that's a lot of products. So I hope if this was chapter 15 and I said, oh, okay, you have this value of K, you'll be like, oh, products are really favored. The forward reaction is really spontaneous. And that makes sense because E cell is a very positive number. All of this points to that forward reaction is spontaneous. Okay, 7 minutes. All right, same redox reaction with the same mistake in it. So change that A to an X. So let's set up this cell at standard conditions. What is the concentration of X plus at standard conditions? 1 molarity. What's the concentration of Z plus? 2 plus, sorry. 1 molarity. So therefore Q is equal to what? 1. So what is E cell? 1.2. Yes, it is 1.2. For funsies, try putting the Nernst equation here, right? The Nernst equation is E cell equals E cell naught, which we were given, minus numbers over N, ln, or no, log of Q. We just got log of Q is 1. What is log of 1? It is 0. So when we are at standard conditions, what we measure is the table value. That's what we just proved. When Q is 1, this whole term goes away. And that's why we can say when we're at standard conditions, doing cathode minus anode, you can do that. And then that's your cell potential, but only at standard conditions. So what do you think the follow-up question is going to be? So here we're at standard conditions, E cell is 1.2. What's the follow-up question going to be? Now we're going to not be at standard conditions, probably. Yeah, okay, what if we double the concentration of everything? Okay, so we started at 1 molarity. If we double the concentration, X plus is now what concentration? 2. Z plus is now 2. What is Q? Are you sure it's 1? Remember, let's look at the equation for the reaction. The expression for Q, is it just simply thing over thing? No, it's not. I did this on purpose. Q, let's just not assume it's 1. Q is the concentration of Z plus, 2 plus, sorry, over the concentration of X plus, but it is squared. So Q is actually not 1. It is 2 over 2 squared. It is 1 and it's a half. Is that a half? Yeah. Okay, so it's 0.5. So are we at standard conditions now if we double the concentrations of everything? No, we're not. All right, so we got to plug that into the Nernst equation. But it's not that bad. We have everything we need. E cell is equal to, so we're using the Nernst equation. E cell naught minus 0.0592 over N log Q. We have all those numbers. So E cell naught was 1.2 that was given minus that number that I always forget. N, what did we say N was? 2 for the reaction, log of 0.5. So these are the concentrations now, or this is the new measured cell potential when the concentrations are doubled given the equilibrium expression. So 1.2 minus 0.0592 divided by 2 times log 0.5. Boom. I get 1.21 volts. Okay, so if I double the concentration, I get a little bit more juice out. Great, just a little bit. Because we're not at standard conditions anymore, all right? So Q is a little bit deviated from 1, so we did change it. So yeah, don't assume that if they're both the same concentration here, because the nature of this equation, Q did deviate away from 1. Okay. Okay. Okay, 2 more. All right. Okay, what if the concentrations are this? So same thing. Sorry, fix that X. What if the concentrations are this? So it's the same thing. Calculate Q. Q is equal to Z2 plus, so 2.0 molarity over X plus concentration, so 0.01 squared. So Q here is that. So, oh, dang, that's really big. So 20,000. Q is real big. So it's the same exact thing. We're going to do the Nernst equation. We are not at standard conditions. So we're going to do E cell, what we actually measure at this concentration. Also think about it. We don't have a lot of product. Or sorry, no, we have a ton of product. We don't have a lot of reactant. So how do you think our E cell is going to be different? Is it going to be bigger than 1.2 or less? It's going to be a lot less because we don't have a lot of reactant. Your battery is almost spent. So 1.2 minus 0.0592 over 2 log a big number, 2 times 10 to the 1, 2, 3, 4, 4. So 1.2 minus 0.0592 divided by 2 times log a big number. I get, it's going to be less. It is 1.07 volts. Yeah, so in this example, we don't have a lot of reactant. We favor more of those products are present. Q is really big. E cell is less. This is like, sometime later after we let this battery run for a long time. We've accumulated a lot of products. Now our voltage is a lot lower. All right, last one. Wow, perfect timing. Okay, so those were the mathematical ways that we can calculate E cell. So what's the trend that we get? When Q is equal to 1, the E cell that we measure is equal to the book value. But when Q is less than 1, we have a lot of reactants present. So E cell is usually greater than the book value because of the Nernst equation. When Q is a small number, we subtract a negative number, and so E cell gets larger, what we measure. But when Q is greater than 1, the cell potential that we measure is less than what the book tells us, that your voltage starts to go down as we accumulate product. That's what we just did in those previous slides. So in these questions, ask yourself, changing or adding or removing these things changes Q how? How does that change your cell potential? So if we add magnesium 2+, first ask yourself, how does Q change if we add a product? Q goes up. So therefore, your cell potential goes down. What if we add magnesium solid? How does Q change? It doesn't. So does the cell potential change? It does not. So Q, no change. So your E cell does not change. No change. Oh, dang, we're out of time, but there's 3 more. Let's just do them. Okay, add HCl. You're adding a reactant, so Q is going to change how? It's going to go. Look for where H+ is in the reaction. Where is it? It's a reactant, so Q is going to go down. E cell is going to go up. What if we add sodium hydroxide? Oh, sodium hydroxide isn't in the reaction, so is there going to be no change? That's not true. Sodium hydroxide does what to this reaction? It actually removes H+ because it's going to neutralize it. So Q is actually going to go higher because you're removing a reactant. And so therefore, E cell is going to go down. So that one's a little bit different. And the last one, if we increase the pressure of hydrogen, that increases Q also, so E cell goes down. All right, so best of luck, everybody. We'll continue on with nuclear chemistry next week, and I'll make a new packet for the final.